Well, hello there. Welcome back. So today we are going to be continuing with our limit set infinity, finishing that up, and pretty much put all the curve sketching behind us. Well, at least we'll be moving away from that with the next lecture. So here's hoping. Cross our fingers we can get through all this. So let's start off with the homework from last week. We had from section 3.5, we had numbers 13, 14, 19 maybe. Let's start with 13. So 13, we were given the limit at x approaches infinity of x squared plus 2 over x cubed minus 1. Alrighty, so that's going to be the limit as x approaches infinity of, well, how do we simplify this? Figure out what this limit's going to be as we head out towards positive infinity. We divide every single one of these terms by the highest power, x. So in that case, it's going to be x cubed. So I'm going to wind up with x squared divided by x cubed plus 2 divided by x cubed over x cubed over x cubed minus 1 over x cubed. Well, that's going to be the limit as x approaches infinity of, well, 1 over x plus 2 over x cubed over 1 minus 1 over x cubed. Alright, now when I apply this limit, this is going to go to 0, this is going to go to 0, and this is going to go to 0. I'm going to be left with 0 over 1, which is 0. So the behavior of this function is that as I head towards positive infinity, it is going to approach y equals 0. In other words, there's going to be a horizontal asymptote at y equals 0. Now, would I get the same thing if I went to negative infinity? Well, let's see. If I do negative infinity, this is still 0, this is still 0, this is still 0, 0 over 1 is still 0. So negative infinity would be exactly the same. So you weren't asked to do that, but just wanted to point out that a lot of times heading to positive infinity and then heading to negative infinity give you exactly the same value. The majority of them by far actually do that. So for part B then, we had, let's see, the limit as x goes to positive infinity of, let's see, x squared plus 2. Yeah, x squared plus 2. Sorry, I was double checking. I think I miscopied it. I'm going to x squared plus 2 over x squared minus 1. I think that's what I should have had down on my paper. So I have this as my problem. That is going to simplify into, if I divide by the highest power x, I'm going to divide everything by x squared now because it's the highest power. So I get x squared over x squared plus 2 over x squared over x squared over x squared minus 1 over x squared. That's going to be the limit as x goes to positive infinity of 1 plus 2 over x squared over 1 minus 1 over x squared. I now apply the limit. This is going to go to 0. This is going to go to 0. I'm going to be left with 1 over 1, which is 1. So I will have a horizontal asymptote at y equals 1. Alrighty, last but not least, I'm going to look at the limit as x goes to infinity of, let's see, this time it is x squared plus 2 over x minus 1. When I divide by the highest power of x, I get the limit as x goes to infinity of x squared over x squared plus 2 over x squared over x over x squared minus 1 over x squared. Okay, so that's going to simplify into, I'll put equal signs here. I'm going to have the limit as x goes to positive infinity of, well, it's going to be 1 plus 2 over x squared, and then all of that over 1 over x minus 1 over x squared. Okay, so this one's a little bit different because when I take the limit, this is going to go to 0, this goes to 0, and this goes to 0. So I'm left with something kind of strange. I have 1 over something that is approaching 0 at the bottom. Well, if the top is a constant and the bottom is going to 0, that means the overall value is going to infinity. So the answer to this is that there is no horizontal asymptote. It is taking off to infinity. So in other words, as you go over in the positive x directions toward positive infinity, it's taking off to infinity. The value, y value, is going to infinity. Okay, no big deal. So there you have it. Depending on how you arrange these powers, if your highest degree is in the bottom, you're going to wind up with a limit equal to 0, your horizontal asymptote at 0. If the powers are the same, you're going to wind up with whatever this ratio is. And if the top power is the largest power, you're going to go to infinity as you take the limit. It's just something to keep an eye out on. So that was part 1 of the homework. So let's go to number 14 for the next one and clear this. So 14, we had same type of setup. We have for part A, we have, let's see, the limit as x goes to positive infinity for, that's a terrible limit, sorry about that, 3 minus 2x over 3x cubed minus 1. Okay, so based on what I said in the previous one, what happens when I have a power that is higher in the bottom? Well, when I divide everything by that power, the only thing that's going to survive is going to be whatever this bottom coefficient is. Everything else is going to go to 0, so it should be 0. Let's see if that works. So I'm going to have 3 over x cubed minus 2x over x cubed over 3x cubed over x cubed minus 1 over x cubed. Alrighty. Oh, that was that, and I forgot to put my limit in front. Oh well. So let me do that right now. Don't want to forget that limit. It's kind of important. The limit as x goes to positive infinity of, well, this simplifies into 3 over x cubed minus 2 over x squared over, I'm going to have 3 minus 1 over x cubed. 0, 0, 0. 0 over 3 is still 0. So we'll have a horizontal asymptote at y equals 0. That's going to be the end behavior for the function as I head out to positive infinity. Okay? I get the same thing if it were negative infinity? Yeah, because this is still going to be a 0, 0, and a 0. So it would still be exactly the same. Now, though, let's look at the limit. As this is for part B. The limit as x goes to infinity of 3 minus 2x over 3x minus 1. Okay, so that's going to be the limit as x goes to infinity of, well, what do we divide by? Well, the highest power is just x, so it's going to be 3 over x minus 2x over x over 3x over x minus 1 over x. All right, that can simplify into limit as x goes to infinity of 3 over x minus 2 over 3 minus 1 over x. Well, when I apply the limit, this term goes to 0, as does this one, and I'm left with negative 2 over 3, which is negative 2 thirds. So if they have exactly the same power, it's just the ratio of the coefficients in front of them. In this case, negative 2 thirds. So there would be a horizontal asymptote at negative 2/3, y equals negative 2/3 for this one. Alrighty. Last but not least, part C, we have 3 limit, hold on, I gotta do my limit as x goes to infinity of 3 minus 2x squared over 3x minus 1. Alright, you want to put any bets down on what this one's going to go to? Since the numerator has the highest power, this is going to blow up to infinity, but we'll see. Limit as x goes to infinity. I'm now going to divide by x squared every single term, so 3 over x squared minus 2x squared over x squared over 3x over x squared minus 1 over x squared. Okay, so when I simplify that, I'm going to get the limit as x goes to infinity of 3 over x squared, same, minus 2 over 3 over x minus 1 over x squared. Okay, so in this case, I'm going to have my 3x over 3 over x squared rather go to 0, negative 2 untouched, 3 over x goes to 0, and this 1 over x squared goes to 0. So this leaves something that we saw before, negative 2 over something that is approaching 0. So this one is equal to negative infinity, because it's going to infinity, but there is a negative sign in front of that 2, so it's going to a negative infinity. Ta-da! Alrighty, so I think that is probably sufficient. I do want to say one more thing about that, though. Okay, how to say this? This one is a little bit strange because of what I have right here in the bottom. I have 3 over x minus 1 over x squared. They're both going to 0, but which one is going to 0 fastest? In other words, one of these terms is going to 0 slower than the other one, and one is going faster. The one that's going to 0 faster is this second term. So this is going to 0 faster than this one right here, which is still going to 0, but it's going to 0 slower. So these values are going to be larger than these values, so the sign attached to this term is going to dominate when I subtract this off. No matter what the signs are, this one will dominate because it is going to be the larger value than this one. This one's going to 0 faster, so it's a smaller value. So if this one dominates the sign, when I head to positive infinity, when I'm looking at as x goes to positive infinity, my y value goes to negative infinity. So to write that out as x goes to positive infinity, y goes to negative infinity. Okay, that's what we found right here. But unlike the others before, now I have a problem, not a problem, a different observation, because if x goes to negative infinity, this value is going to be a negative value. It is going to be a negative value underneath a negative 2, which means that I'm not going to wind up with a negative infinity that y is heading to. I'm going to head to positive infinity, like that. Okay, so this is not something you're going to see very often. I just want to point it out that in this case, it actually does matter whether or not we're going to positive or negative infinity. it changes which direction the y heads to. It. If you graph this out, you'll see that it does hold. As x goes to positive infinity, the y goes down, so it's hitting something like that. And then as it heads to positive infinity, to negative infinity, this way it's going to take off like that. So it does something like that. Alrighty. Now, let's knock out the last of the homeworks. Clear the screen. So let's see, for 19 we had the limit as x approaches infinity of 7x plus 6 over 9x minus 4. Okay, now that was my f of x. I asked you to, instead of doing the instruction in the book, to actually try to go through every step and graph this out, because it actually does pay off. So if we do that real quick, this one doesn't take long. Step 1, are there any discontinuities? Yes, there are. Because when I set 9x minus 4 equal to 0, I can solve out and when with x is equal to 4/9. Okay, that is where I have a vertical asymptote. Okay, so step 2, f prime of x. Well, f prime of x, this is a quotient, so it's going to be the bottom, 9x minus 4, times derivative of the top, which is going to be what? 7 minus the top, 7x plus 6, times derivative of the bottom, 9, and then all of that over the bottom squared. So 9x minus 4 quantity squared. Well, that's going to give me 63x minus 36 minus 63x plus 54. Okay? So that looks good to me. Wait, that's not 36. That's 28, isn't it? So they're looking at the values going, that doesn't match what I have on my paper. 28. There we go. I agree with that one. So, and all that is over 9x minus 4 quantity squared. So 63x minus 63x gone. Negative 28 plus 54. F prime of x is going to equal 26 over 9x minus 4 quantity squared. Okay, so interesting. Part A, then, this is finding the critical numbers, right? Probably should have mentioned that so I can stay using the same pattern that I did before. So part A, are there any discontinuities? Well, we already knew about them, didn't we? They're at x equals 4/9. So already knew, already known, AK. And then part B, f prime of x equals 0 implies that 26 equals 0. No solution. There are no critical numbers here. Okay, so if there are no critical numbers, what about my f prime chart? Well, there are no f prime of x equals 0, so I don't have to worry about that. So I am going to skip that. Alrighty, so now we go to step 4, and we're going to do clear the screen. So for step 4, we want f double prime. Well, f prime, let me do the work over here, f prime of x is equal to 26 over the 9x minus 4 quantity squared. Okay, now I can do a rewrite on this and make this 26 times 9x minus 4 to the negative second power. The reason I want to do that is because that makes f double prime of x really easy to find. Because then f double prime, well, this is just a power chain, so this becomes negative 2 times 26, negative 52 times 9x minus 4 to the negative third power times what? 9? Yep. Alrighty. So now I just need to figure out what this is. negative 52 times 9. I'm getting, oh, and then it's going to be over 9x minus 4 to the third, right? So negative 52 times 9 is negative 468, if I did that math right, over 9x minus 4 cubed. Wasn't that an easier way to find that? So if you get lucky and you wind up with just a number on top of your f prime, for your double prime, rewrite it and just do the power rule. Way, way, way easier. So part A, these are for my inflection points, right? My inflection points. So part A, any discontinuities? Well, we already knew about them. Same place as always at x equals 4/9. So part B now, f double prime of x equals 0 implies that negative 468 equals 0, which is not true. So no solution. There are no inflection points, which means that for step 5, the chart, f double prime chart, skip it. There is no need for it. We have no inflection points. All right, now we move to our y values. Okay, that's where we're going to plug in our critical numbers and our inflection points, but we don't have any. So skip. There are no y values to worry about. Okay, so now we clear the page and we're going to move on to step 7. And step 7 now is going to be finding the horizontal asymptotes. We do that by taking the limit as x goes to infinity of our f of x, which was 7x plus 6 over 9x minus 4. Now, after having done a few of these, you can probably already tell that we're going to have a horizontal asymptote at 7/9, but let's go ahead and go through the steps. So this is limit as x goes to infinity of 7x over x plus 6 over x over 9x over x minus 4 over x. This is going to go to 0. This is going to go to 0. This is going to go to 7. And this is going to go to 9. 7/9. It's going to be my horizontal asymptote. All right. So now we can graph this thing. I need to take my discontinuities, graph every one of them. So I have a vertical asymptote at what, 4/9? Is that right? Yep, 4/9. So I'm just going to say that this is 1, and actually not. Let me not make that one. Let me make this one 1 over here. I don't want to make that one 1 because I want to have a little bit of room. I'll make that one 1. All right, so 4/9. It's somewhere around here. And then my horizontal asymptote is at 7/9. So it's somewhere like that. Okay? Now, I know that I'm either going to have this behavior or this behavior. So where I either have both slopes negative or both slopes positive. So what I need to do is figure out what that's going to be. Alrighty, so let me get rid of this. There's a lot of stuff on the screen earlier. So where do I look for slopes? I look for slopes in my f of prime. In my f of prime. In my f prime, not f of prime. What was my f prime? F prime of x was equal to 26 over 9x minus 4 quantity squared. Okay? Now, no matter what values I plug in for my x here, it's going to get squared, so it will be positive. Positive over positive is positive. So I know my both slopes are positive, so it has to look like this. And that's it. That's how it should look. Ta-da! Okay, we're done with homework. Now we can start the main stuff. So here we go. clear this. Let's get started. Okay, so up to now we've been saying that limit as x approaches infinity is usually the same thing as limit when x approaches negative infinity. And that's because in a lot of these cases we're using this limit behavior to change something like this into a zero. So it doesn't really matter whether it's approaching zero from the left or from the right. So a positive or negative zero, if you will. But there is one spot where that is not the case, and you will always have to take both of these kind of separately, and that's when you have root functions. So root functions. So if I have something that looks like 3x minus 2 over root 2x squared plus 1. Okay, if I have that, pad head. I'm going to scratch on my mouse pad. Anyways, not important. I don't care about that. But a function where I have a root function where it's something, a root of something squared down here, I need to be really careful when I think about what's going on, because in order to divide every single term by the highest power x, a couple things. The highest powered x is an x squared down here. That x squared is under a root, so it's really like saying the root of x squared, which is approximately x. So if I were going to divide by the highest powered x, I would want to divide every term by x, and so I would have 3x over x minus 2 over x, and this is where I run into some trickiness. So 2x squared plus 1 under a root divided by x. Now, how do I get this x inside the root in a way that will make sense and be legal, if you will, for math? Not the most dramatic way to say that, but that'll work. So I need a way to kind of backwards translate into this root x squared. So if I change this x into 3x over x, hold on, let me get all this written down, minus 2 over x square root 2x squared plus 1 over, and then I do root x squared. So that right there is going to work in a way, because now, since it's a root over root, I can make it one big root. But we run into a kind of a semantics problem, it's a logic problem, in that if I look at, I'm going to just draw a little thing to the side here, the limit as x approaches positive infinity, and do that substitution, x equals x squared. Everything's fine. That works 100% because I'm looking at my x values here need to be approaching positive infinity, so it's a positive number, and I'm going to get a positive number if I square a value and then take the root of it. The problem kicks in when I look at the limit as x approaches negative infinity. I can't use that same logic because I'm looking for an x that I know is negative. This value right here is approaching negative infinity, so it's a very large negative number. But if I take that value, square it, and then take the square root, now it's a positive number. So when I'm looking to do a substitution so where I can get a root of an x squared so that I can make this one giant root and then be able to divide every term by the appropriate value, I need to change this substitution. If I'm looking for x going to negative infinity, I want to do a substitution of x equals negative root x squared. This only works if I'm approaching the negative infinity, because this says that it's a very large negative number, and that is equal to taking that number, squaring it, rooting it, and then putting a negative sign in front of it. That is correct. So the two substitutions that I'm going to do are going to be this one if I'm heading to positive infinity, and this one if I'm heading to negative infinity. Okay? So let me show you how it would work. We're going to pick up right here. I'll do the original, and then we'll pick up right there. So let me clear the screen. So the original was 3x minus 2 over, we had root 2x squared plus 1. Okay? So I wanted to find the horizontal asymptotes using the limit. So I'm going to do the limit as x approaches positive infinity for 3x minus 2 over root 2x squared plus 1. I'm going to also put the limit as x approaches negative infinity of 3x minus 2 over root 2x squared plus 1. Okay? Well, I need to look at both behaviors. I need to know what happens at the far left and the far right, what the behavior settles down to. So I'm now going to get to the point where I had the limit as x approaches infinity of, let's see, I divided every term by x, and I had 3x over x minus 2 over x, and then I had the root 2x squared plus 1 divided by root x squared. That's correct. Now when I want to look at the limit as x approaches negative infinity, it's going to be 3x over x minus 2 over x over root 2x squared plus 1 divided by negative root x squared. Okay? So now that I've got it set up with the appropriate substitutions, I can make this one big root. So this is going to become the limit as x approaches infinity of, if you allow me, 3 minus 2 over x divided by big root 2x squared over x squared plus 1 over x squared. Okay, because I can always take root a divided by root b is the same as big root a over b, right? Using the root properties. So now I've got them all in one root. Okay, and so I'll do the same over here. It's going to be exactly the same, except there's going to be a negative sign out in front. So this is going to be 3 minus 2 over x over 1 big root 2x squared over x squared plus 1 over x squared, and don't forget the negative sign out in front. So now this one is going to settle down. I think I can fit all this on here. Limit as x goes to a positive infinity of 3 minus 2 over x over, here we go, I think I can squeeze all this in. I'm going to have 2 plus 1 over x squared. Hope that all fit on. And then over here I would have the limit as x approaches infinity. It's going to be 3 minus 2 over x over negative root. And what's in the root? 2 plus 1 over x squared. Okay, so now I can apply the limit. This is going to go to 0. This is going to go to 0. So I'm going to be left with 3 over root 2. That will be what it is approaching as x approaches positive infinity. On this side is going to be 0, 0, negative 3 over root 2. Okay? So I have two different horizontal asymptotes. One as I approach infinity from, if I go to the right infinity, as the function heads far, far, far to the right, it's approaching 3 over root 2. And in this one, as I go to negative infinity, it's going to approach y equals negative 3 over root 2. Okay? So when you have this kind of setup where you have a root and it's an even root underneath like this, you have to, when it's an even root of it's an even root of an even value underneath, you're going to wind up with these two substitutions taking place. One of them is going to be positive root x squared. The other one is going to be negative root x squared, or the equivalent, if depending on what the root degree is. So you're always going to wind up with one direction it's going to be one value, the other direction it's going to be the opposite sign value. So let's do an example of that. I think it'll be a lot clearer. So let me clear this. And before I forget, let me actually sketch that for y'all so you can see what it looks like. We're going to say that this is positive root 3 over, positive 3 over root 2. And down here is going to be negative root, or 3 over root 2. Okay? So I've got a horizontal asymptote, something like that, and the same thing down here. If I graph that function out, and the function was 3x minus 2 over square root of 2x squared plus 1. If I graph that out, I wind up with a graph looking something like this. This is going to look kind of strange. But it does this, and then it does, if I can sketch this properly, this. Okay? Now, this is very strange behavior if you're used to vertical asymptotes. So a vertical asymptote is a missing value. It is something that makes the denominator go to 0. So it is undefined. So, I mean, I can do this, I can do this, and all the other variations, but you will never see the function leap over. No matter how I graph it, it will never cross the vertical asymptote. That is not the case with the horizontal asymptote. A horizontal asymptote is not trying to find where there's a discontinuity. The horizontal asymptote, all it's looking for is the limit behavior as x goes to plus or minus infinity. It just wants to know what the function settles down to as it heads out to positive infinity and negative infinity. So it is completely free to cross the asymptotes before it gets to these end values. You know, this behavior right here in this chunk, that is behavior that's nowhere near the infinity, so we don't care about what it's eventually going to settle down to in this immediate nearest neighborhood. But at infinities, it settles down, it never crosses this asymptote coming from the bottom, and same thing for this one. When it heads to negative infinity, it is not going to ever cross this value coming up from the bottom. So that's just something to keep in mind. Vertical asymptotes and horizontal asymptotes are completely different animals. A vertical asymptote is a value that is a discontinuity, so you will never have the function crossing it. A horizontal asymptote is just the end behavior as the function heads out to positive infinity and negative infinity. Okay? So I just wanted to make sure that was kind of talked about a little bit because I don't want to have problems with going, oh gosh, we crossed it. We can't do that. No, it's perfectly fine to cross a horizontal asymptote. All you're looking at for that is the end behavior. So, alrighty, let's do an example now. Let me clear this off. So, our function is going to be f of x equals x over root x squared plus 2. Alrighty, so first things first, is this going to have any discontinuities? Nope, there are no discontinuities to this. Why? Well, because I'm squaring whatever value of x I put in here, which makes it positive, and I'm adding a positive to it, and so the answer has to be positive. So root of a positive is never going to have a discontinuity. So that's good. And then for the second one, if I'm looking at the derivative of this, well, before I do that, I'm going to do a rewrite because it's going to make my life easier. X over x squared plus 2 to the 1/2 power, like that. So f prime of x is going to be bottom, which is x squared plus 2 to the 1/2 power, times derivative of the top, 1, minus the top, x, times derivative of the bottom. Okay, so this is going to be 1/2 x squared plus 2 to the negative 1/2 times the derivative of the interior, because that's the chain rule, 2x. So it's going to look like that. Then all of this is over the bottom squared. So if you'll allow me, I'm going to write it as 2/2. That will let me do something that I want to do. So do you remember a while back we did a simplification when we were doing the derivatives by dividing every term by either a plus 1/2 or a minus 1/2 exponent? Do y'all remember doing that? And it turned out one of the ways made things complicated, one of the ways made it super easy. So when you're in a situation like this where you're taking the first derivative of something that had a root, square root in the bottom, you want to, once you get to this stage, divide every term. This is going to make your life simple. Otherwise, the math is not fun. Divide every term by x squared plus 2 to the, you remember? Negative 1/2, right? If I divide by the negative 1/2, here's what happens. If you remember, if I have x to the 1/2 divided by x to the negative 1/2, you subtract exponents when you're dividing them. So 1/2 minus negative 1/2 is the same thing as 1/2 plus 1/2, which is just going to be x to the first. Okay? So when I'm dividing by a negative exponent, it's pretty much the same thing as adding it to the top exponent, because I'm subtracting the negative. So if I think about it that way, when I divide every term by this factor here to the negative 1/2, I'm going to add 1/2 to each of these exponents here. So this is going to become a 1. When I divide x squared plus 2 to the negative 1/2 by x squared plus 2 to the negative 1/2, this whole term becomes a 1, because it's just the same thing over itself. And this term right here, this exponent right here, is not going to be 2/2 anymore. It's going to wind up being 3/2. Okay? Now I'm going to write it out the long way one time and work it out one time, and then, well, won't do that again. We'll just do this shorthand. So x squared plus 2 to the 1/2 over x squared plus 2 to the negative 1/2. This is what I did up here, but in long form, minus x times 1/2 times x squared plus 2 to the negative 1/2 divided by x squared plus 2 to the negative 1/2 times 2x, and I can move that negative 1/2 factor here that I'm dividing by to any of these pieces because they're all multiplied together. I'm just moving it where it belongs. And then all of that is going to be over x squared plus 2 to the 2/2 divided by x squared plus 2 to the negative 1/2. So that's where it happened up here. This becomes an x squared plus 2 to the first. This becomes just a 1, and the bottom is going to come to 3/2. Okay, so I'm going to start right back with this. I'm going to clear this and start back over. So I've got f prime of x equals I'm going to have x squared plus 2 to the first power times 1 minus x times 1/2 times that whole thing simplified to a 1 times 2x, like that. And then all of that is over, well, it's a stray, or kind of weird. Where did that come from? X squared plus 2 to the 3/2. Okay? So, now that I've got this ready to go, I can simplify this a little bit. So this is going to become x squared plus 2, and this is going to become x times 2x times 1/2, so the 2 and the 1/2 cancel. So this is just going to be minus x squared, and then over x squared plus 2 to the 1/2 power. Okay, so when the dust settles, I'm going to have x squared minus x squared, so they're going to be gone. So my f prime of x is going to equal 2 over x squared plus 2 to the 1/2 power. Okay? So now what do I do with this? Well, I can now find my critical numbers. So A, are there any discontinuities here? And that should be to the 3/2. Oh, let me forget that, not to the 1/2, to the 3/2. Okay, so there are no discontinuities again because I am squaring, and so it's always positive, adding a positive to it. And then when I take the square root, it's still going to be positive. So no discontinuities. But if I do f prime of x equal to 0, if I'm looking for my critical numbers, my horizontal slopes, that implies that 2 equals 0, which we know is no solution. So there are no critical numbers for this equation. Alrighty? So that means that for step 3, my f prime chart, I can skip it. So skip. Okay? Now, I can already tell you I'm going to want to know what slopes are at the end, but I can come back to that. Right now, I'm just going to skip the f prime chart. So now let me go to the next one. So clear this. Step 4, looking for my inflection points. And that occurs when f double prime of x equals stuff. So I need to find f double prime. Well, to find f double prime, I need my f prime. So I've got f prime of x is equal to 2 over, here we go, x squared plus 2 to the 3/2 power. I'm going to rewrite this into a different form, which will be way easier to differentiate as 2 times x squared plus 2 to the negative 3/2 power. Now I can find this second derivative by doing a power rule. So if I do that, I'm going to wind up with, let me start here, f double prime of x is equal to, well, it's the exponent times the coefficient in front of it, so negative 3/2 times 2, just to make sure that that 2 isn't forgotten, times the function x squared plus 2 to the, well, I'm going to subtract 1, so negative 3/2 minus 1 is negative 5/2, and then I have to multiply by the derivative of the interior, which is 2x. Okay? So this factor right here, the x squared plus 2, is going to be in the bottom, but everything else is on the top. So I can simplify this. Those 2's cancel. I have negative 3 times 2x is going to be double prime of x, negative 6x over x squared plus 2 to the 5/2 power, just like that. So way, way, way easier than doing the quotient rule. If you have just a constant up on top, you can always do a rewrite and change the derivative into a power rule rather than doing the full quotient. But it only works if there's only a constant on top, because if this had a variable, I couldn't do it. I have to use the quotient rule if there's an x up on the top. But since it's just a constant, I can do this rewrite, do the power rule, and it's way easier to find the derivative. So now that I have my second derivative, I can look for, there are no discontinuities, again, and now I can look at f double prime of x equals 0. Well, that implies that negative 6x equals 0, which means that x equals 0. Thank you so much. Alrighty, so now that I've got this set up like this, I've got my inflection point, and I can move to step 5, which is the f double prime chart. Okay, so x equals 0, I need a value less than that. So how about x equals negative 1? So f double prime of negative 1, what does that look like? Well, f double prime is right here. This is always positive because what we talked about before. If I plug a negative 1 in for the x right here, it's going to get negative times a negative, so that'll be positive. So that means it's positive, which means it's going to be concave up. Okay, now a value greater than 0, so maybe x equals 1, positive, and then it will be a negative on top, so f double prime of 1 is negative, which means it's concave down. Alrighty, so we're ready to move on to the next step. Let me clear this. So let's see here. Let's say, let's see, the sixth step is the next step. So those are the y values. I only have one I have to look up. And so that one is the inflection point we just found. So I'm looking for the value at x equals 0. Well, my original function was, what was it? Gosh, I have to remember what that was. So the original function was x over square root of x squared plus 2. So I have f of x is equal to x over root x squared plus 2. Well, I plug a 0 in. The top goes 0, bottom doesn't, so that's a 0. So my inflection point occurs at the origin. Alright, but wait, there's more. Step 7. Now let's see what the end behavior is going to be like. So I need to find the horizontal asymptotes. So here we go. This is where we did all this for. I'm looking first for the limit as x approaches positive infinity of x over root x squared plus 2. Well, I'm going to divide every term by the highest power x, which in this case is just plain x. So this is going to equal the limit as x goes to infinity of x over x over root x squared plus 2 over x. Now I can do that substitution. So this is going to be the limit as x approaches infinity of 1 over, I'm going to have root x squared plus 2 divided by positive root x squared. Since I'm heading to negative 2, since I'm heading to positive infinity, it's going to be positive root x squared. So now I can combine that into a single root, so that equals the limit as x approaches infinity of 1 over 1 big root now, x squared plus 2 divided by x squared. So now I'm going to distribute limit as x goes to infinity of 1 over big root x squared over x squared plus 2 over x squared. Now I can apply the root if I want. I guess I got to do one more simplification. Limit as x approaches infinity of 1 over big root 1 plus 2 over x squared. Alright, now I apply the limit. This term goes to 0. The others don't. I'm going to be left with 1 over root 1, which is positive 1. Okay, Now I need to look at the limit as x approaches negative infinity. So everything's going to be exactly the same except for right here, because now I'm going to have a negative sign in front. So this is going to be 1 over root x squared plus 2 divided by negative root x squared, since I'm heading to negative infinity. So this is going to be the limit as x approaches negative infinity of 1 over, if you allow me, I'm going to just pop that in and simplify it. So this is going to be negative, one big root, I'm going to have x squared over x squared plus 2 over x squared. And I can do one more simplification, limit x goes to negative infinity of 1 over negative root 1 plus 2 over x squared. Now I can apply the limit. When I do that, this term goes to 0. I'm left with 1 over negative 1, which is, if I can fit that in, equals negative 1. So as I approach infinity to the positive side, the horizontal asymptote is at y equals 1. As I go to negative infinity, the horizontal asymptote is at y equals negative 1. Okay, so what does this thing look like? Well, let's clear this and sketch it out. So clear the screen. Here we go. Sketch. Okay. We have an inflection point at 0, 0. And I have two horizontal asymptotes. That's all I have. Well, I have one more bit of information, but I'm going to save that for just a second. So at 1, I've got a horizontal asymptote, and at negative 1, I've got a horizontal asymptote. Now, this horizontal asymptote is the positive one is as I'm going to positive infinity, and this one is as I'm heading to negative infinity. I've got an inflection point at 0, and I have no horizontal slope, so I do not have to worry about anything like I had with that last example where at the bottom it kind of went up like that. I don't have that now. So I have a very simple looking graph. All I have to do in order to be able to figure out if it is this graph or this graph is the thing about what concavity I had. My concavity, when I did my F double prime chart, said that I was concave up and concave down. That means this graph has to look like this. Concave up, concave down. And turns out that is exactly what this looks like. So there you go. Hooray! We did it. Oh, I know it's a lot of work, but those horizontal asymptotes really give you your end behavior, and they are, you have to have them. Some functions cannot be graphed by hand without thinking about that end behavior. So there you go. So let's clear this and move on to the next thing. So the last thing I want to talk about before I give you the homework really quick is the limit as x approaches positive infinity of sine x over x. So we had this a long time ago when we were first doing limits. We did a squeeze theorem and we came up with what this limit actually was. But let's talk about, if we think about it from a perspective of a horizontal asymptote, okay? So this function right here, the sine x, it is limited to values that are between negative 1 and 1, right? Whereas this x down here is heading to positive infinity. So what's going on with this function? Well, if I graph it out, I actually get something really nice looking. I wind up the function looks like this. It just goes flat with the, assuming I can actually draw that. Just pretend that I can draw a straight line. So what happens is, well, basically what happens is that the sine function is decaying down to 0. And that's what we should expect right here, because what happens is I've got a value that can only range between -1 and +1, and I'm dividing it by infinity. That is actually settling down to 0. It's going to oscillate as it settles down to 0. It's going to go up, down, up, down, up, down across the x-axis, but that is where it's heading. And this is yet another kind of indication that if I have a horizontal asymptote, the horizontal asymptote is looking for this end behavior here. It is not concerned with crossing around up and down and over the horizontal asymptote. It's just thinking about what's happening at the very tail end as you head up to positive infinity. So that was just a nice little way to think about, now that we've dealt with horizontal asymptotes a little bit, kind of what is going on with this function here, this limit as x goes to infinity of sine x over x. And it's really approaching 0. That is what the horizontal asymptote behavior is going to be as it heads out to positive infinity. So hopefully you like that. Now homework is just going to be, it's going to be a little bit odd, a little bit of a challenge. 2.5, numbers 20 and 26, and 2.6, 26. So 2.6 is just, it's called curve sketch summary. And all it does is it just does more complicated examples of the things that we've learned in 2.3, 2.4, and 2.5. So first derivative test, second derivative test, and horizontal asymptotes. So 26 is a little bit tricky, and some of the problems in 2.6 incorporate very strange looking functions. I mean, you've got some functions that look like, oh, that was the worst sketch I've ever done in my life. Try that again. I'm not making this up. Some of the functions look like that when you graph them out. So once you get to 2.6, some of the functions are very interesting because it has behavior that you've got a min here, you've got horizontal asymptote, you got vertical asymptotes, you got all sorts of things going on. So for when you finally get to 2.6 and you're doing the summary curve sketching, I highly recommend that you graph it out in Desmos first, and then kind of let that guide you as you go through the process of steps 1 through 8 to finally do the sketch by hand. Alrighty, so tackle these. These are not trivial problems, but they are good ones, and I will see you next time. Take care. Bye-bye.